Welcome back to Multigrid Methods, a mostly matrix-based approach. So I'm going to talk more about why I call this a mostly matrix-based approach as we move into the further chapters 4, 5, 6, um, and uh, and why also I'm calling it mostly or not completely matrix-based approach. So there is a reason behind my naming it in that way. And you might be wondering what it is. I will uh, I will definitely explain my rationale especially once we get to chapter 5. So that's coming. For now, we're still stuck in this idea of two-grid, and we're trying to prove the convergence of the two-grid algorithm. Last time we were working through this Fourier analysis. In particular, we're trying to figure out what are the standard operators, standard matrices that we've defined. How are they transferring modes from one grid to another? Last time we proved that the restriction matrix, which remember takes fine grid functions and maps them to coarse grid functions. So, by the way, I'm not going to make any kind of distinction between talking about a function and its coordinate representation. Basically, they're the same thing. Remember, the idea is anytime we want to talk about a coordinate representation of something, that's a vector, and we usually write it like this. Or if I want to specify that it's on if I want to specify the fact that it's on some generic level L, I'll say it like this. So that's connected to a finite element function, which we'll call VL through the basis BL. And of course, the finite element function is going to live in the space capital VL. That's the space of piecewise linear continuous functions with zero boundary conditions, etc. And of course, this guy over here lives in is just a vector. So I won't make any distinction between these objects, which are vectors, and these objects here, which are functions. So whenever I say the restriction operator, the restriction matrix takes a function, this, of course, you view it as a vector um, in this way, but we can think about it as a function. So what we needed to do with our modal analysis, our Fourier analysis, is figure out how the restriction operator moves modes or moves functions on the fine grid to the coarse grid. And in this case, we're really interested in these sine waves or modes. How does the restriction matrix move a mode, a sine wave, on the fine grid down to the coarse grid? Well, it does it in a sort of funny way. But think about it like this. This is a fine grid function, a mode on the fine grid, and it can be of low frequency or high frequency. So whenever we talk about low frequency and high frequency, it's usually and it's most logically with respect to the fine grid, in this case, the one grid. So this can be a mode, sine wave of either high frequency or low frequency, and it gets mapped down to the coarse grid. Once we get down to the coarse grid, really the only thing that can exist down on the coarse grid are what were low frequency modes on the fine grid. So if the thing started out as a low frequency mode to begin with, then it gets mapped to a low frequency mode on the coarse grid with a prefactor of 2 in this typewriter CK, and CK was defined along with SK as it's just the cosine of K pi h1 over 2, and SK was equal to sine, I guess with a square, K pi h1 over 2. So it gets mapped down to a mode on the coarse grid with this prefactor of 2. We explained the prefactor of 2 was because our restriction matrix is kind of producing things which are 2 times too big, times this cosine squared term. And if the mode starts out in this range, that means it's a high frequency mode, then it gets mapped to the coarse grid using aliasing by flipping to a reciprocal wave number, k prime. So the k prime for these high frequency modes are all going to be low frequency, which is good. So this is how it gets translated into a low frequency mode, and it gets transmitted with the prefactor of -2 sine squared k prime pi h1 over 2. Okay, so we proved that last time. The proofs of this in this section are simultaneously easy and hard. Easy in the sense that it's just trigonometry, and hard because the trigonometry gets to be a little bit complicated. So this one we established last time. Now we need to understand how the prolongation operator moves modes from grid to grid. So we keep in mind the prolongation operator takes us from the coarse grid. So the prolongate, if it's a kind of like a diagram, it takes us from a vector on the coarse grid, which is a short vector, and it's going to map it to something in the fine grid, which is a long vector, or in other words, has a lot of degrees of freedom. So something which with a few degrees of freedom, think like n0 equals 3, to something with n1 equals 7. So we're working from the coarse grid to the fine grid. So the question is going to be, how does it move information? Well, the information that we're interested in are modes on the coarse grid. And so K here has to be a mode which can be viewed on the coarse grid. And those modes are the low frequency band of the spectrum, K between 1 and N0. Okay. Well, of course, all the frequency values, all the wave numbers that you can experience on the coarse grid. It's just that the wave numbers that are associated with the fine grid uh, and that are classified as high frequency don't make any sense on the coarse grid. So again, we're interested in K between 1 and N0 getting pushed up to the fine grid. Whenever that happens, we get some modes which are pushed up, okay, to the same frequency, and some modes which gets transmitted to the reciprocal wave numbers, K prime. So this is what we want to show in this next result. So here's how we're going to do this. Let's suppose that I can be any number or any index between 1 and n1. So let's think about this. What I'm going to do is I'm going to start off with this vector on this side. So where does this vector live? This vector is on the fine grid, right? We start off with, so our domain is the coarse grid, but we end up in the fine grid. So this vector has components I from 1 to n1. So that's where we're going to start. However, it turns out it's useful for us to bin these into two separate bins. So let's suppose that I plus 1 is odd, or sorry, I is odd, then I plus 1 is even, and we can divide that by 2, and I'm going to get a whole number out, which I'm going to call j. However, if I is already even, then I'm not going to add anything to it. I'm just going to divide by 2. That also gives me an integer, and that's what I'm also going to call j. And of course, j is different values depending on whether or not I is odd or even. And of course, I can see that you can get repeated j values. So let's look at this. So whenever I have I, 1, 2, 3, 4. So what are the values of j coming out from that? Well, the first I is odd, so we're going to add 1 to that. Divide by 2, we get j equals 1. The second one, I is already even, right? And so we're not going to do anything to that but divide by 2, and we get 1 out in the end. The third value of I is odd, so we add 1 to that. That gives 4, divided by 2 gives 2, and so on. Right, so these this is not one-to-one mapping, right? Because 1 goes to 1 and 2 also goes to 1, right? And 3 goes to 2 and 4 goes to 2. All right, but this is just a way of counting that's going to be useful for us momentarily. So just keep in mind that for these I values, I'm going to get out J values, which aren't necessarily unique. And as I said, I want to start with this side and then prove that I end up with this. Okay, so I'm showing these two things are equal, so I'm going to take this vector first and then show that it ends up being equal to this. Now, remember, what was the definition of the prolongation matrix? So that matrix had to be tall and thin, and it had entries like this, etc. Right? That's not a very good drawing because it's going way down. Oh my goodness, my. All right. Continues like that. So that's what the prolongation looks like. So I'm going to start with this guy and try to show that what I get is looks like multiplication of vectors using these rows. So there's the thing that I want to start with, thing on the right-hand side, which is this vector ck v1k minus sk v1k prime. And I'm going to look at the ith component of these guys. Remember, this is a vector on the fine grid, so its components go from 1 to n1. Now, it is a fairly simple little calculation to do this. Again, every time I say simple in the context of these trigonometric computations, it is simple in the sense that you're just using trigonometry and basic algebra, but it gets a little bit tricky because the trigonometry is complicated. So I claim that using 6, which was, what was 6? I apologize. I didn't realize I'd have to go so far back. Where are you, 6? Okay, looks like I somewhere deleted 6 on the way. No, here we go. Using this identity, right? That identity 6. And some basic trigonometry, we can show that this, keeping in mind, we know what these guys are. These are just sine waves. So I can combine them together. If I is odd, I'm going to get out cosine k pi h1 times sine k pi x1I. And if I is even, I get out, or I find that I get sine k pi x1I. So that's an exercise for you guys to do. It's not that difficult, but it is rather tricky. And it's probably 4 or 5 lines going from this to this. So I get out 2 different answers according to whether or not I is odd or I is even. So you use that aliasing formula, which I just referenced, 6, and you also have to use a sine angle summation identity. All right, so the next thing I want to do is I'm going to keep this guy pretty much as is. The only thing I'm going to recognize is that since I is even, then this is equal to 2j. And this one here, because I is odd, I can convert this guy, I, to 2j minus 1. Okay, just based on my definition of j. Next thing I want to do is use a sine angle addition formula again to operate on this guy. This looks like it's well, what I can do is use the sine angle addition formula with respect to this guy here. Notice that this is going to be, I'm going to use the fact that x1 2j minus 1 is equal to, that's h1 times 2j minus 1 So this is 2j times h1, which is x1 2j plus h1. So I'm going to use that fact, and I'm going to I'm going to use that fact, okay, to write this as the summation of two angles, or the sine of two angles, and then I'm going to use another trigonometric identity to convert that to this line that you see here. And then I realized that this, through some further simplification of trigonometric identities, that this line becomes 1/2 sine k pi x1 2j and 1/2 sine k pi x1 2j minus 2. All right, so the important thing here is that this guy has a 1 in front of it, and this guy has two 1/2 coefficients in front of it. So if I go back to my matrix, then basically I'm getting out this row and this row, or this row and the next one, which is going to be 1/2 1/2. And so what this shows is that, according to whether or not I is odd or even, that I get the rows that I would expect to get from the prolongation matrix. This one or this one. The only one that's a little bit weird is this guy here. There's only a single 1/2. However, I can treat this as if it's 1/2 ghost cell over here. And this one down at the bottom is going to be 1/2, but I can treat the second one as if it's going to be 1/2 there. Now, the reason why that works out is because the 1/2 that I'm multiplying here is just going to be essentially 0. And the same with this. The 1/2 I'm going to introduce here is going to be essentially 0. So this confirms then that through this calculation that what I'm getting are the individual rows of the prolongation matrix, okay, according to whether or not I is even or I is odd. So I shown then this is essentially all the possibilities for the prolongation matrix acting on this mode. And so that shows that this is equal to that, which is what I wanted to show. All right, so we'll put that in our pocket. So that takes care of the prolongation modal analysis. We've done the restriction modal analysis. The only thing left to do is the modal analysis for the error transfer. So let's do that one next. To do this one, there's two parts. And it turns out for the second part, which I'm not going to do, I'm going to throw to a homework exercise. It's useful to know two extra aliasing results. So now I'm going to abuse the notation aliasing. Aliasing for us really means that if we apply a trigonometric to something here involving a reciprocal wave number, then it gets transferred to a trigonometric of some argument without the reciprocal wave number, just the ordinary wave number. So any any identity like this, we're going to refer to as an aliasing result. So put these two things in your pocket. You're going to need these to prove the second result for this or the second part of this next result. The first one is that the sine of this reciprocal wave gets transferred directly into a sine. And if I take the sine of k prime pi h1 over 2, then that gets converted to cosine k pi h1 over 2. And again, there's really all this involves is inserting the formula here for the reciprocal wave number, which for us is, at least in this section, is going to be n1 plus 1 n1 plus 1 minus k. So just insert that formula in, use the sine angle summation formulas, and you get these results coming out. So put that in your pocket. You're going to need that for the second part of this, which I'm not going to do in class. So namely this one. So the one I'm going to do is this guy. So we need to understand how the error transfer matrix Well, this is an error transfer for the coarse grid Ritz projection, or the error of the coarse grid Ritz projection. We need to know how this matrix I minus pi 1 tilde is going to map modes into modes. So let's think about what this is. This is a square matrix, and it acts on vectors in or on the fine grid. It's a square matrix, and so it maps things from the fine grid to the fine grid. And I claim that the result of this, at least for the low frequency modes, is going to be that this mode, this low frequency mode, gets mapped to a low frequency mode with a sign pre-multiplier. So this typewriter notation SK means, as I said before, SK is sine K pi H1 over 2. And by the way, if you see a prime here, that just means put the prime there. And the same with the cosine or the C function. The C function is just, by the way, this should be square. The C function is just the square of the cosine. So it gets mapped to this guy, which is the low frequency mode. Okay. Low frequency gets mapped to a low frequency mode plus SK, which is again this factor here. This guy gets mapped to a reciprocal wave, right? So this guy is actually a high frequency mode. Similarly, if I'm interested in starting out with these modes here, so this mode looks like, I'm using K prime here, but I'm using K prime with K being in the low frequency range. So this actually means K prime is a high frequency wave. So this is telling me how I'm mapping high frequency wave numbers. That gets mapped to another high frequency wave times a prefactor of cosine K, or cosine squared K pi H1 over 2. That's this guy. Plus this guy, which is my aliasing result. So I'm going to show this one, and this one I'm going to leave for an exercise. All right, so the way we prove this is we're assuming here that A0 satisfies the Galerkin condition. This just means that the A0 matrix is exactly like the A1 matrix. It has the same eigenvalues and eigenvectors. The only difference being that every appearance of an H1 gets replaced by an H0 for the low frequency case, or for the coarse grid case. The definition of the coarse grid Ritz projection, pi 1 tilde, is going to be P A0 inverse. This represents the fact that on the 2-grid algorithm, I'm taking an inverse on the coarse grid times the restriction matrix times the A1 matrix. And as I said, A0 satisfies the Galerkin condition. That just means that A0 is equal to R times A times P. And this really means that the matrix A naught is similar in structure to the A1 matrix, and it has the same eigenvalues and eigenvector structure. So let's just get started with this. We'll break this guy up into its constitutive parts. We'll start by assuming that we're dealing with the low frequency wave numbers. Okay, so we need to know how this low frequency mode gets mapped to other modes. And we know, according to the result, that what we get is some combination of low frequency modes and high frequency modes through aliasing. All right, so the first thing we're going to do is attack this V1K vector with A1. Well, this guy is a mode. It's a sine wave, and it's precisely an eigenvector of A1. So what I get in return is I get this guy back with an eigenvector, or sorry, an eigenvalue, lambda 1K. Okay, so this guy goes away and it just yields V1K, lambda 1K, eigenvalue, eigenvector. So now I need to know, how does the restriction operator map this fine level mode to other modes? Well, we know how that works. If this is a low frequency mode, equation 7, which tells us what is the action of these restriction matrices on modes. That says that this gets mapped to 2ck times v0k. All right, so that takes care of the restriction matrix. That was equation 7, right there. So now I have V0, and pre-multiplying that is A0 inverse. Well, this is an eigenvector of the A0 matrix, and it's also an eigenvector of A0 inverse, right? It's just going to produce an eigenvalue associated to that guy, but it's reciprocal, and that's where that guy comes from. So that takes care of the application of A0 inverse. And finally, I have to multiply the prolongation matrix times this mode. And let's see, this is a mode on the coarse grid that is of low frequency. Actually, it's low frequency with respect to the high or to the fine grid, but it's representing all the modes or all the frequencies on the coarse grid. So how does this action work? Well, we proved that the result of this action is to produce that vector. CKV1K, so it gives us a high frequency, or sorry, the low frequency mode back with a prefactor of CK, and through aliasing it produces this vector. Okay. So that's from equation 8. All right, so we're almost done. Now we simply have to figure out, well, maybe what is the value of lambda 1K over lambda not K? So I claimed through some simple algebra, lambda 1K over lambda 0K, well, that is just the high frequency eigenvalues versus the low frequency eigenvalues in the low frequency range when I reason with respect to the high or to the fine level grid. That is, K here is between 1 and n naught. So I get 2, I think it's, is it 2 or is it, no, it's 4 times sine squared over h1, and I get sine squared that argument times 4 over h naught. Okay. So this guy, I've done a conversion here. So why am I using h1 here instead of h0? Well, it's h0 over 2, h0 over 2, but that's just h1. So I'm using here that h 0 over 2 is just equal to h1. So I took care of a replacement there. I'm not actually using these forms of the result. I'm using the sine squared versions of the result. Those 2's or 4's, whatever they were, cancel. So I have h0 over h1. The next thing I'm going to use, the fact is that, well, again, I'm going to use h0 over 2 is equal to h1, or in other words, h0 is equal to 2h1. So that springs force this 2. This guy is just my sk notation, and I get sine squared k pi over h1 on the bottom, which is something I didn't have any extra notation for. All right, so that takes care of my eigenvalues or the ratio of those eigenvalues. So for my first term, let's see, where does this guy come from? I have this ck out in front. I've just found this ratio. So I get 4ck sk coming from that, over sine squared k pi h1 times this is what I had just from the brackets previously. Then I recognize that through the half angle identity formula, the formula that I'm actually using here is sine k pi h1 is equal to 2 sine k pi h1 over 2 times cosine k pi h1 over 2. So the half angles are here and here. They're the same half angles. They add up to this. So the sine summation formula gives us this half angle identity. I can divide both sides by 2, and then I can square both sides, and then I get this result here. So that comes from that result over there. So I'm going to substitute this in. I immediately see that I get a lot of cancellation. In fact, I just get a cancellation of those two terms. That's just a 1. And so what I'm left with is ck v1 minus sk v1k prime. And again, I'm interested in the low frequency range as it relates to the spectrum of the fine grid. Well, this is almost what we need. What we're really interested in is I1 minus that. And so to do that, I'm just going to subtract this result from V1K. So for those low frequency modes, then I'm just going to do a V1K minus that last result. So V1K minus this last result, that gives minus CKV1, or 1 minus CKV1 times quantity V1K. And the minus becomes a plus. So now it's plus SKV1K prime. Well, this is 1 minus cosine squared of an angle, and that just gives the sine squared of that angle. So I get sine squared of the same angle, and I can pull that out. And that gives me the result that I wanted. So the result I wanted was this one, even though I didn't actually use a distributive property to pull that guy out. It's clear that I can do that. To prove this guy, there are a lot of ways that you can do it, but I'm going to skip that and make it a homework exercise. What you need to know is basically you're going to trudge through the same sort of results. The only difference is you're going to use the high frequency end of the spectrum, and so that you have to pay attention to the only difference in the analysis, or at least the first difference that you find, is when I apply this result here, the restriction matrix, to this guy. If it's high frequency, then I don't get the prefactor of 2ck. I get minus 2 sine, or minus 2 sk. This ck becomes sine squared k. So that's the difference. So you have to use that fact, and then you have to use the aliasing results that we introduced as a technical lemma before this theorem. And so that's equations 9 and 10. Okay, from this aliasing lemma. All right, so I'm going to leave that as an exercise. You guys can take care of that. Just want to make sure that you understand all that's going on. Again, this trigonometry turns out to be rather tedious. It's not, because it's so tedious, we can kind of lose our way by doing or thinking about the trigonometry. We really want to focus on what the actions of these matrices on these modes actually mean. Well, we're going to get to that right now because we're going to talk about the convergence of the two-grid method. So this is the main theorem of this whole chapter. And it says that ultimately, if I use this two-grid algorithm, then I'm going to be guaranteed a convergence. And here's the sense in which it's going to be guaranteed convergence. The first thing is, let me get out of the way that we're going to use only one particular form of the two-grid algorithm. Remember, in the two-grid algorithm, there was this pre-smoothing step and a post-smoothing step. We're going to shut off the post-smoothing step because it turns out it's not going to be necessary for us. So we set post-smoothing to be 0 by setting M2 equals 0. We don't need it. Okay. Later on, we're going to do an analysis involving an energy method where we need that guy to be exactly equal to M1 so that we have a symmetry. But this non-symmetric version is perfectly fine for our current needs and the analysis that we're going to perform here, this Fourier analysis. This is kind of the simplest analysis that you could possibly do. As I said, other forms of the analysis that we're going to do later are going to require the symmetry, namely the energy analysis. All right, so remember what's happening here. So we have an error transfer matrix that transfers the error from our two-step algorithm from one iteration level to the next. All right, so we know exactly what is the form of this guy. We're going to write that down momentarily. And let's see. What we're going to do is we're going to take the level 1 norm. By the way, this does not mean the 1 norm. By putting the subscript 1, it means that we're doing the 2 norm, but on the 1 level. Okay, it's the usual Euclidean norm on the fine grid level. So what we're going to show is that this is less than or equal to some prefactor, which I'm going to call gamma M1, which is completely independent of H. Completely independent of H times E1L. So what this shows is if I can prove that this prefactor is always less than 1, then I'm going to get a contraction. Well, that's exactly what I'm going to prove. I'm going to show that this prefactor, which is just this guy here, is always less than 1. And moreover, it doesn't degrade as H gets smaller and smaller. It doesn't degrade as H1 gets small. It's completely H1 independent, so it doesn't degrade as H1 gets small or equivalently as N1 gets large. It's completely independent of those two numbers. It only depends on the number of pre-smoothing steps that I do. And I'm going to show that this number is less than 1, strictly less than 1, provided that I choose my M1 to be 1, 2, or 3, or actually any positive integer. So that's what I'm going to show with this, the convergence of the two, for the convergence of the one-sided two-grid algorithm. It's called one-sided, by the way, because we're shutting off the post-smoothing. We're only doing pre-smoothing. So how can we prove this? So the proof is going to be based on an eigenfunction or eigenvector expansion. So let's expand the iteration level L error. Okay, this means error at iteration L on the one grid or on the fine grid. And I'm going to expand that in a basis of eigenvectors for the stiffness matrix, V1K. So probably should have written this depends on L here, but since we're only doing one step, that doesn't matter too much. So I'm going to drop that. Okay, the L here is not the level number. It's going to be the iteration number in my two-grid algorithm. I couldn't use K because K now means for us wave numbers or modes. So this is a basic eigenvector expansion, and these are the eigenvectors of the stiffness matrix. All right, the error transfer matrix E1, which transfers error from the iteration level L to L plus 1, is what we're calling E1. And for the two-grid scheme, that's exactly equal to I minus pi 1 tilde times K1 M1. Now you might say, wasn't there a K over here as well? So this was K1 star M2. But M2 is a power here, and it's set equal to 0. And so if I take the 0 power of this matrix, I just get a 1, or the identity. Okay, so that's where that guy went to. So this is our complete error transfer matrix. And notice that I've lost the symmetry that I proved or established in chapter 2, because the only way I get a symmetric one is symmetric in a certain sense is whenever I have a balance of my smoothing on each side. So here I'm only using the one-sided method, but it's perfectly fine. All right, well, if I have this eigenvector expansion in eigenvectors of the stiffness matrix, then to find out what E1L plus 1 is, I'm just going to multiply this error transfer matrix times this expansion here. And if I do that, then clearly I get the expansion with these coefficients of this matrix, error transfer matrix, times these modes, these sign modes. So now everything boils down to figuring out what the heck is going on with this. Well, I claim in our previous result, we figured out what this guy does to modes. And we already know what this error transfer matrix for the smoother does to modes, because we specifically showed that the eigenvectors for this guy are the eigenvectors of the stiffness matrix, and we calculated what those eigenvalues are. Okay, so now we can, by our modal analysis that we did earlier, okay, we have two separate results. So we figured out what is this guy applied to a mode and what is this guy applied to a mode whenever we're dealing with modes that are low frequency versus modes which are high frequency. So this is written in terms of K prime, the reciprocal reciprocal wave number. But here I have K between 1 and N0 plus 1. So this is the low frequency range. That means whenever I take K prime, I get high frequency values. So this is my low frequency result, and this is my high frequency result. And the only difference here is that, well, this guy here maintains the modes, but it's just going to add eigenvalues for this smoothing matrix, this error transfer matrix for the smoothing process. Remember, we called those guys mu1, right? Mu1 and mu1. In fact, this will give an eigenvalue of mu1 k raised to the m1 power, and this one is going to give mu1 k prime raised to the m1 power. All right, so that's exactly what these guys are here. Now, this guy from our previous result, from our just the very last one. Remember, this gives numbers, which is going to be sk times this vector. All right. So once I hit this guy with this error transfer matrix for the smoothing error transfer matrix, I get the same thing back plus an eigenvalue associated to that. And then we know what this guy does to those modes. So ultimately what I get in the end is alpha k times v1k plus v1k prime, where alpha k is equal to, these are the eigenvalues coming from the smoothing process. Remember I said mu1k m1 power. And in this case, I'm using omega equals omega naught. Remember what omega equals omega naught was? That's just 2/3. And similarly for the high frequency modes, I'm going to get a beta k prefactor on these vectors. And the beta k is going to be mu1 k prime to the m1 power times ck. So this comes from the smoothing part. So that's smoothing, acting on these modes here, these k prime modes, these are modes with the reciprocal wave numbers. And then the last result tells me how this error matrix maps these modes. And that gives this times that. Okay, so this is just a combination of two things that I already know. I'm also, previously, I only kept track of k up to n0. I can actually add n1 here, and it still holds true. And the reason it holds true is there's some sort of symmetry involved. So I'm not going to explain that in any great detail. I just want to point out that I've indexed this one more up above what we previously proved, up to n0 plus 1 for those low frequency modes. And this result still turns out to be completely true. Okay, this result here, 13. 14 is there's no change here. Okay, and that's addressed here, that change in 13. But as I said, I'm not going to talk too much about that. Now, what we need to do is we need to apply our some information that we know about the smoothing process. So that's the next step. So remember we said that if I choose omega equals omega naught, then all of the high frequency modes are damped by the factor of a third. That was in fact the reason why we chose omega equals omega naught in the damped Jacobi method. So this is just a statement of exactly that fact. All of the high frequency modes going all the way from n0 plus 1 up to n1. And by the way, just so that you remember, n0 plus 1 is equal to n1 plus 1 over 2. That's the relationship between the fine grid numbers and the coarse grid numbers. We said that all of the high frequency modes in the smoothing process are damped by a third. That was the reason for choosing omega naught. All other frequencies are, all that we know is that they're less than or equal to 1. Okay, for all other frequencies or all other wave numbers, we simply know that the eigenvalues of the error transfer matrix for smoothing are less than or are less than 1, strictly, okay? So now we need to estimate alpha k and beta k. So I'll remind you what alpha k was. Alpha k is just that, beta k is just this guy. And we're going to take advantage of the fact that the sine and cosine functions are never greater than 1. That's all that we really need to use in this very sort of primitive analysis. So for this guy, alpha k, that's just going to be alpha k. What kind of modes are we dealing with? These are the low frequency modes. Okay. How do I know that? Because k is between 1 and n0 plus 1. So these guys, at best I can say is they're less than 1. What if I take to the m1 power? Well, that's less than 1 to the m1 power, which is just the same as 1. So there's not much I can do with this guy. What can I say about sk for those low frequency modes? Well, I can prove that that's less than a half. Okay. So I guess, to be honest, I am using something a little bit more than saying that these are less than 1. I'm going to use that they're less than a half. So that's my approximation for the low frequency end of the spectrum. What can I say for the beta k's? These were for the high frequency end of the spectrum because these involve k prime. So those are high frequency. But I'm simply going to use, this is going to look like high frequency. The k is still restricted to the low frequency end, but remember, k, if it's in the low frequency range, the reciprocal wave number is in the high frequency range. Okay, so this is still low frequency, but this guy is going to be high frequency for the beta k's. Well, because it's in the high frequency end of the spectrum, I can say that every wave number is less than 1/3. Mu has, well, let me just say it this way. Mu 1k is less than in absolute values 1/3. So that's what I'm going to use here. I'm going to raise to the m1 power because that eigenvalue is raised to m1 power times ck. And the best I can say for ck, because that really is in the low frequency ranges, that is less than 1. Now, it turns out I can represent the error vector at iteration L. So this is my 2-grid iteration number. This can be represented in the following way. So remember, I started off by representing it just in a very standard way. But what I'm going to do is I'm going to use the fact that these guys, these frequencies can be numbered according to whether they're high frequency or low frequency. So I'm going to break them into the high frequency parts and low frequency parts. And then I'm going to count the high frequency parts by using the k prime vector. Okay, so that's just going to give me, yield this guy. So notice I'm only summing from k equals 1 up to n0 plus 1. So I'm only summing in the low frequency range. The reason why I'm getting everything for the error vector here is because I'm summing these guys via this reciprocal wave number. So this gives me my high frequency components. This gives me my low frequency components. I'm just adding them up in a kind of different way. Now I have to add a delta k And the delta k is 1/2 whenever k is equal to n0 plus 1, and it's 1 otherwise. The reason why I have to add a half whenever k is equal to n0 plus 1 is because I'm actually counting these things twice. All right, so whenever k is equal to n0 plus 1, then k prime is exactly equal to n0 plus 1. So really, when I get up to k equals n0 plus 1, I get the same thing twice. So I'm double counting that, and the way to take care of that double counting is just to divide by 1/2 by introducing that. Okay, so this turns out to be or make life quite easy. So if I use that, then let's see, this one is not too hard. If I use this expansion, then if I calculate E1L plus 1, well, that's just the error transfer matrix of the two-grid algorithm multiplying that vector. And that guy passes along through here and attacks these guys. And now I know what the values of these guys are once it gets multiplied by that error transfer matrix. That was just tabulated previously. Okay, just these guys here and here. So I'm going to use 13 and 14 with this expansion here, and I immediately obtain this expansion. Not too difficult to show that. Okay, so this alpha k and beta k come because of the application of the E1 matrix. And again, I'm double counting, so but I'm only double counting whenever k is equal to n0 plus 1, so I'm dividing by 2 to take care of that. Now, whenever I want to calculate the 2 norm on level 1 of that matrix, or sorry, that vector that I just defined here, right? Then what I really need to do is take the inner product of that vector with itself. All right. So when I do that, what I notice is that I actually get the expansion. So throw in the expansion that you just calculated here into these two entries of this Euclidean inner product. Well, that's going to mean that I'm going to need to know what these modes are. Okay, if I have, or what I need to know what is the situation whenever I take one mode inner product against another mode. So a mode with index or wave number I against a mode with wave number j. And I claim that what you get there is you get delta ij, that's the Kronecker delta symbol. These guys are not they're orthogonal, but they're not orthonormal. And I have to take it into consideration what is the value of the normalization. Well, it turns out whenever I is equal to j, then what I'm going to get in this case is just n1 plus 1, n1 plus 1 over 2. So that's the normalization factor. So I'm going to plug in the expansions that I got here into these entries of this inner product. This is the Euclidean inner product on level 1. That's what that notation means. And I'm going to leave it as an exercise. It's kind of, I would say, a two-pager, two-page exercise to show that what you get after inputting that is this guy. It's a tedious calculation, but it's not impossible to show this. I think I can do it now in probably 4 lines. It might take you 2 pages because you haven't seen the calculation before, but you're going to take advantage of the fact that writing it in this way proves to some or gives you some sort of interesting advantage. That's about all I can say without going through the details. So I'm going to let you prove this fact. Once I get it to this stage, now I'm going to employ those estimates that I had previously. So I'm trying to calculate the 2 norm squared of this vector. All right, so I'm going to apply first the algebraic geometric mean inequality. So I'm going to apply that to epsilon k prime. And I'm going to say that's equal to or less than or equal to 1/2 times epsilon k squared plus epsilon k prime squared. So that's the algebraic geometric mean inequality. So apply that first. This term here was just epsilon k prime. I can replace these with their absolute values. That gives me something larger. So replace that with absolute values. And now I'm going to do my estimates. Now I'm going to leave these guys alone. These guys are just the coefficients in the expansion for the error at the previous time step at the not time step, but the previous iteration step L. I previously showed that this is less than a half. This is less than 1/3 to the M1. And this is less than a half and less than 1/3 to the M1 power. Okay. And of course you have to take into consideration some of these you're squaring, right? So that's where the squares come from. All right, so that's what I get on replacing those with their estimates gotten from knowing what the smoothing does. So this is, at this point, we're taking into consideration smoothing. All right, this is just a collection of terms. So I'm going to take this one to the next page and do some manipulation of that. Notice that I've gotten two terms out now, ek squared times a collection of numbers and ek prime squared times the same, well, something which is similar. Not exactly the same, okay, because this guy is 1/2 squared. You know, this is not exactly the same. This term here is the same, right? So I want to make these two terms the same so I can extract that common coefficient. Well, I'm going to replace, to do that, I'm going to replace the 1/3 to the M1 power by a half. 1/2 is larger than this guy for any M1. Well, think about it. If M1 is equal to 1, then it's true. If M1 is equal to 2, this is 1/9. It's still true. So this is kind of a fairly coarse estimate, but I'm going to replace this guy using that estimate. So that gives me that allows me then to show where it becomes clear at that point, then these two estimates can be made the same. And I can extract the common value out. And the common value then just becomes this. All right. Now I'm going to take, let's see. Let me make sure of that. So let's see. We have 1/2 squared. Let's see, where am I getting? Oh, right. So this guy now is going to be less than a half squared, right? 1/2 squared. Why did I guess I'm replacing this 1/2 squared with just a half. Is that right? What am I doing here? 1/2. Oh, right. There was no half out here, right? So what I'm getting is 1/2 squared, 1/2, a 1/2 squared, a 1/2. I'm pulling a half out. Okay, so that's where this extra 2 comes from. And then this is the common factor which I'm extracting. What's left here, we recognize in our estimate, is just the Euclidean norm of E1L, Euclidean norm squared. That's just this guy. And we showed that previously. So what I end up with is the Euclidean norm squared of the error at L plus 1 is less than a constant times the Euclidean norm of the same thing, but at the iteration level L. Okay, squared. So now take the square root of both sides, and the square root gives me this gamma m, which I introduced on the first page. So that's what I called gamma m1. All right, so this is ultimately what I'm proving. So we got this through doing what? So careful estimation of how, well, actually, this wasn't even an estimate. We carefully went through and saw how this guy converts modes on the fine level grid. And then, of course, the second aspect of it was we figured out how the smoothing worked. And so what sort of estimates do we get out from smoothing? So it was the combination of those two features which gives us this estimate. Well, now let's think about what this estimate says or is. Well, this estimate is some number. Ultimately, we have to take the square root. The important thing is this number does not depend on H1 or N1, the size of the fine grid. The other important point of this is that if M1 is greater than or equal to 1, then this number is a number less than 1. If we take the square root, we get a number less than 1. So on the next page, I'm going to tabulate what these values are. So they're independent of H1 and N1, and they're numbers which depend on M1, but become smaller up to a point, and are all less than 1. So here are the values that you get for this. So on the top line, I'm listing M1 values. So take it to be 1, 2, 3. So these are the number of pre-smoothing steps that I do. Okay, so the number of smoothing iterations, relaxation steps that I do for each time I do an application of the two-grid algorithm. And these are the values that I get out for gamma M1, right? After taking the square root. So if I start off with M1 equals 1, then it's going to be 1/2 plus 1/3 square root, and that value is just going to be 0.91287. So that's okay. I mean, that's a number which is independent of H1 and N1 and is less than 1. So that's going to lead to convergence, right? That gives us a contraction of that error. But we can do better. If we take M1 is equal to 2, then we get a better contraction factor of 0.78176 and keep going. If we take 3, then we get 0.73283. So the point is we want this number to be small, less than 1, and as small as we can possibly make it. Well, it turns out we can't make it infinitely small, because if the larger we take M1, the closer it converges to 0.70710, the square root of 2 over 2, essentially. Okay, so that would be in the case where we make this infinitely small by making M1 large, which we could do, but it turns out that doesn't give us a lot of bang for the buck of our computational dollars. So what we usually do is we say, okay, well, I'm not going to, doing more smoothing iterations costs a lot of money, so I'm not going to go all the way out to infinity. I'm going to stop somewhere around 3. And if I stop at 3, then I get, something which is not super awesome, but it's certainly less than 1. It's certainly independent of H1 and N1. And so that's all I really need. Okay, so that guarantees that I have this convergence of this two-grid algorithm. Let's show that we get this convergence with some computational examples. All right, so now we want to go through a couple of computational examples which show this convergence in some experiments. So the experimental setup is this, if you want to call it an experiment. It's a computational experiment. We're trying to solve this equation, right? And this results from the discretization of our usual suspect, u double prime equals f, with u of 0 and 1 equals 0. So we get this through finite element discretization. This A1 is our finite element stiffness matrix. And the f is our forcing vector, which comes through in the finite element case by integrating the right-hand side f against the basis functions. In this case, we're going to assume that we know what the exact solution is, and we're going to compute, we're going to manufacture a right-hand side vector, f1, by multiplying a1 times the true solution. Okay, so we assume we have a true solution, multiply by the stiffness matrix, and that gives us a candidate f1. So now we know what the true solution of this problem is, right? Because we just gave the true solution to it. But now we're going to do some computational some computations where we forget that we know what this true solution is, and we use our two-grid solver to get an approximation. So we're going to initialize our two-grid solver by choosing a pseudo-random or using pseudo-random numbers. I guess this guy here should actually be, I think that should just be 0. This should just be U1, 0. There's no brackets around that. So what I mean here is that this is just going to be a vector, and I take all of the entries of that vector to be chosen by random numbers. So in experiment 1, we're going to use our optimal smoothing parameter, omega equals 2/3. We're going to use M1 equals 3, so we're going to use the one-sided two-grid method. We're going to shut off post-smoothing and only use pre-smoothing, and we're going to use kind of what the results suggest should be optimal. Just use 3 because that's going to save our computations, okay? And then what we're going to measure is, as we go through computations, we're going to measure the difference between the true solution, because because we actually have the true solution, we can compute the exact error, okay, as L gets larger and larger. So this is what we observe. The true error is going to 0 rather rapidly. Notice that this is a semi-log scale. So on this axis, we're plotting the norm of the error in the 1 norm. So this just means the Euclidean norm on level 1. And this axis is in the log scale. So notice that this is going to 0 quite rapidly, right? So by iteration number 8, it looks like we've already got an error which is less than 10 to the minus 8. By iteration number 9, it's getting close to 10 to the minus 10. That's the exact error. And so what we do with this is we're taking the last 4 last 4 errors that we compute, and we're doing a log linear fit. And we're computing, well, what is the reduction in the error that we observe? Well, it turns out the reduction in the error, this computed reduction, actually turns out to be a whole lot better than what the theory is suggesting. Remember, the theory suggested we should get something around 0.7. Actually, we're getting something which is basically 10 times smaller than 0.7. So it's 0.07. That's really rapid convergence. And notice N1 is equal to 255 in this case. It doesn't matter what we take N1 to be, we're always going to find that we get the same rapid convergence. Basically, this contraction is 10 times larger than what it was predicted to be. Okay, 0.07 instead of 0.7. This is showing what happens to the error after we do certain steps of the code. So if we look at what happens after smoothing, what we notice is that we get rid of high frequency noise or high frequency components of the error. But then after we do the coarse grid correction, it squashes that error, but it introduces back high frequency noise. So this becomes a little more obvious when I show you what happens whenever we take the number of smoothing steps to be larger. So let me see. I'm going to use an experiment 4. I'm using a lot of smoothing steps. Now this is kind of wasteful in my algorithm, but I want to show you this because it's going to show you exactly what's happening as we do more and more smoothing. So as we do more and more smoothing, it's making this error vector very, very smooth. Okay, so what happens in our algorithm is we, I guess this is iteration level 1, and this is iteration 2 on our coarse grid, on our two-grid method. So what we do is we take our initial error, we smooth it, and we get a very smooth error because we're doing a lot of smoothing steps. And then we apply the coarse grid correction, and the coarse grid correction adds back a lot of error. Well, not a lot of error, it adds back high frequency components of the error. Now notice that after doing that coarse grid correction, the error does get reduced. So here it goes from something like 1.5 to 0.005. So it really is reducing a lot of the size of the error, but it introduces back high frequency modes of the error. Then we go from here up to here. We take this information down here, we smooth it, and that removes, you can see it kind of looks like it's doing what it's supposed to do. It's removing the high frequency components of the error. So this is after smoothing, and then we do coarse grid correction. It reduces this again, and it reduces it in magnitude. Smoothing doesn't reduce the error in magnitude much, but it does make it very smooth. But once we pass it through the coarse grid correction filter, it really reduces this by a pretty large amount. In fact, in this case, it's reducing something which is something like 3 times 10 to the minus 3 to 1 times 10 to the minus 4. So it really is contracting it. All right, so I'm going to stop there, and we'll pick up with these computational experiments next time. I'm also going to go through a little bit and show you what the code is doing and what the code looks like. So that's written in MATLAB. You can already get that code from the GitHub directory. It's there and you can play around with it. I think it's already set up to do these experiments. So go ahead and try these experiments if you're computationally minded and interested, and you can see how things are working. So I'm going to stop there and I can take any questions that you guys have.